Here we have a car wheel that initially rotates at 52 radians per second. That is going to be the initial angular speed. After braking for this amount of time, the wheel is at rest. What does that tell us? That tells us that omega final is 0. And we want to find the wheel's average angular acceleration, which is alpha. So if we go to our angular kinematics equations for constant acceleration, we can see that we are looking for alpha. There's alpha, there's alpha, there's alpha. So this equation up top, not going to use that one because it doesn't have alpha in it. And we have omega initial, and we've got time, and we've got omega final. You know what? I don't think I'm even going to look any further. I think I'm going to use this top equation right here without that part of it. Alpha is equal to omega final minus omega initial, whole thing divided by time. Alpha equals omega final minus omega initial divided by time. That's going to be 0 radians per second minus 52 radians per second divided by 7.3 seconds. You can see that this number is going to come out negative and to two significant figures, which is what we need to round to because of the quantities that were given. I got negative 7.1 radians per second squared. What does that angular acceleration mean? Well, what it means is, since we chose initially our angular velocity to be positive, when the angular acceleration comes out negative, that means that the wheel is spinning slower and slower and slower, which is exactly what's happening. What about the next part? What's the wheel's angular displacement? Now, which variable is angular displacement? That's going to be theta. Once again, let's go to our kinematics equations. So there's theta right there. This equation doesn't have theta in it, so I'm not going to use that. There's a theta right there, and there's a theta right there. There's a theta down here as well. But this deals with arc length, and we don't know anything about the radius of the wheel, so I don't think we're going to use that equation. So the question is, which of these three should we use? Well, we know the final angular speed, we know the initial, we know the time, so that equation would work. We could use that one for sure. And we just found the angular acceleration, and we know the initial and final angular speed, so that equation would work. We know the time, we know the angular acceleration, we know the initial angular speed, so that equation will work as well. It really doesn't matter all that much which of the three you choose. However, I'm going to choose the one at the top. And the reason I'm going to choose the one at the top is because this one right here involves alpha. And so does this one near the bottom. You see that? I've drawn arrows that are pointing to alpha. And if we use either of those equations, then we will have to use this negative 7.1 radians per second squared, which we just found. If we use those equations, and if we have somehow made a mistake calculating this negative 7.1, then our new answer will be wrong as well. Sometimes you can't get around that. Sometimes you have to use a previous answer to calculate something new, but here we don't have to. So we're going to go back to the original givens, which are that the time is 7.3 seconds, the final angular speed is 0, and the initial angular speed is 51. We're going to use this equation up here that I've boxed in, and we're not going to bother calculating that part of it. We're just going to use that. One more time. Sometimes you can't get around having to use a previous answer to calculate something new, and there's nothing wrong with doing that. You just need to know that there is a danger that if you use a previous answer to calculate something new and you've made a mistake on your earlier answer, that error could propagate to the next one. Here we go. Angular displacement divided by time is 1/2 omega final plus omega initial. We want to solve for theta, so that means we're going to need to multiply both sides by t. If I just get rid of that there and put the t there, is that all right? What does that give us? 1/2. The final angular speed was 0, so you know what? I think I'm just going to put an x through that, because that was 0. The initial angular speed was 52. I'll go ahead and put the unit there, radians per second. And the time, what was it? It's the same as right here, 7.3 seconds. The second units cancel. Look at that. That gives us the unit radians, which is just what we want. Calculate this out, round it to 2 significant figures because that's what we were given. And I got 190 radians. That's the angular displacement of that wheel over that amount of time. What about the magnitude of the angular acceleration of the Earth as it spins on its axis, and then also as it revolves around the sun? What does angular acceleration mean? First of all, that's alpha. If something has an angular acceleration of 0, its rotational rate is not changing. Something that has an alpha of 0 sounds either like this, that is, it's not making any sound because it's not rotating, or if alpha equals 0, it might sound like this. Constantly spinning, not changing in pitch. If alpha is something non-zero, then something is going to sound maybe like this, like that, or that's an alpha that's not equal to 0. Well, the Earth is spinning at a constant rate. It's going around the sun at a constant rate. So alpha for the Earth, both spinning on its axis and revolving around the sun, is 0. It's not speeding up or slowing down.